This is week 16 notes, factoring special case trinomials. So special cases are coming in two cases, factoring perfect square trinomials and then factoring the difference of two perfect squares. Let's do some examples. Of special case 1, and by the way, we have already learned this before. I'm just presenting it in a different way to you. X squared plus 10x plus 25. Now, I want to ask you to factor this, okay? And we've already factored things like this. However, this is going to take an interesting form when we factor it, and I'll just use it to point something out. So we're going to look at this number right here, 25, and find the factors of it. We have 1 and 25. We have -1 and -25. We have 5 and 5, and -5 and -5. Now, which one of these pairs right here? We have 4 pairs, 1, 2, 3, 4. Which one of them, when you add them together, they add to positive 10, right here? Well, let's see. I'm looking and I'm seeing 5 and 5. So that means that that will lead us to our answer. When we split x squared into factors, we get x and x, so that when we write our answer, we're going to get x plus 5 times x plus 5. Now, another way that I've actually pointed out before that we can write this is x plus 5 quantity squared. Why is that? Well, it's because we're multiplying x plus 5 by itself, so that must make sense, right? This is called then a perfect square trinomial. We got it by multiplying x plus 5 by itself. Let's do another example. It's going to be x squared minus 12x plus 36. And again, I would encourage you to try this on your own before we do it. Okay, so when we think about factors of 36, I think about, of course, 1 and 36. I think about -1 and -36. Think about 2 and 18. -2 and -18. There's 12 times 3. But I'm also looking at 6 and 6. Let's see. Oops, I kind of did that wrong here. 6 and 6, -6 and -6. And when I'm going through all these factors, -6, I am trying to see which pair adds to -12 right here. If you pick -6 and -6, you'd be right. So our answer is going to be x minus 6 times x minus 6. The x and the x coming from the factors of x squared. But another way to write this is x minus 6 quantity squared. So again, folks, this is a perfect square trinomial. Excuse me. Why? Because we took x minus 6, multiplied it by itself to get it. Just something to point out. Sometimes you can identify these perfect square trinomials by looking at the last number and just seeing, is it a perfect square? Meaning, did you multiply a number by itself to get this number? And when you think about that and ask yourself, is it a perfect square? And you say, yes, it is. 36 is a perfect square. 25 is a perfect square. Then it's pretty easy to find what your factors are to factor it. All right, special case number 2. This is the factoring of the difference of two perfect squares, okay? Examples of perfect squares, just because I think maybe some of you are a little rusty on the topic. I'll just give you some number examples of perfect squares. 1 is a perfect square. 4, that is a perfect square. 9, 16. Do you see where I'm getting these? All right, I'm going to keep writing them and maybe you can figure it out. 25, 36. Can you think of the next one? 49, 64. Can you think of the next one? 81, and 100. And that's as far as I'm going to go. Now, how did I get these? Well, each of these numbers is a perfect square because I took a number and multiplied it by itself to get it. So what did I multiply by itself to get 1? Obviously, I multiplied 1 by itself. So what I'm going to do is I'm not going to write 1 times 1. I'm just going to write 1 squared. Okay? 1 squared. That means 1 times 1. So 1 squared equals 1. What squared equals 4? That's 2. 2 squared equals 4. What squared equals 9? 3 squared. 4 squared equals 16. 5 squared equals 25. 6 squared equals 36. 7 squared equals 49. By the way, the numbers that are perfect squares are not the 1, 2, 3, 4, 5, 6, 7. The numbers that are perfect squares are the 1, 4, 9, 16, 25, 36, and so on. All right, 8 squared is 64, 9 squared is 81, and then 10 squared is 100. So you can see that these are all perfect squares. Now, terminology, square root. What is that? You probably heard it before. What is the square root of 100? Well, the square root of 100 is 10. The square root of 81 is 9. The square root of 64 is 8. What's the square root of 9? 3. What's the square root of 36? It's 6. Okay, the square root is the thing that we multiplied by itself to get the perfect square. All right, so that's just some terminology. Now, why are we doing that? I'll show you in just a second, but before I do that, I need to show you some examples of perfect squares in the variable form. X squared, that's a perfect square. Why? Because we multiplied x by itself to get it. Y squared, that's a perfect square. We multiplied y by itself to get it. Any variable squared, that is a perfect square. Any variable squared. Also, you can have x to the 4th power. That is a perfect square. How is that? Well, it's because we multiplied x squared times x squared to get it. Anything we multiply by itself will yield a perfect square. Okay? Now that I've defined what a perfect square is, let's look at the formula for factoring the difference of perfect squares, and then I'll show you a different method for doing it. So the formula for factoring the difference of perfect squares is the following. You have one perfect square. So this would be, okay, let me back up. This would be an example of a question you would get. You have one perfect square, let's just call it a squared minus b squared, okay? Plug anything in you want for a and for b. Could be a variable, this could be a, this could be 2 or 3 or whatever, you know? But the way to factor this is the following. It factors into the following. A, you have an a there and a b there, a there and a b there, okay? That's where the a squared comes from, then you have the b squared. Watch, it goes plus minus, or minus plus. One of them's positive, one of them's negative. One of the b's are positive, one's negative. That's how this factors. So for example, in like a question that you might get, if I was to give you like a squared minus 16, how would you think about that? Well, you know that 16 is a perfect square because I defined it as 1 up here. And then a squared is a perfect square. Why? Because it's a multiplied by itself. So both of these are perfect squares, and you have a minus sign in between. So if you have that, that means you can follow this difference of perfect squares formula and just plug it in, plug it in. So a squared minus 16 can also be thought of as a squared minus what squared? Well, 16 is 4 squared. And then you can just plug things in and follow this formula, okay? So that is a, we'll put a in the a spot, and then minus 4 squared. So see how we had minus b squared over here, and we just put b there, plus 4 minus 4. And we just followed the pattern, okay? What's another example? You could have a squared minus 36. Are these both perfect squares? Yes, they are. And is there a minus sign in between? Yes, there is. So because of that, we can follow the formula for difference of perfect squares. We would think of this as a squared minus 6 squared. And then we would just write it like this: a plus 6, a minus 6. And we're done. It's factored. We didn't have to go through that whole thing that we learned before because this is a special case. And when you can identify special cases, it just makes it that much easier to factor things. But if you want to do it the old way, you can. So let me show you how to do it the old way. Let's take, for example, a squared minus 16. How would we do this the old way? Well, we have to give it a middle term, right? So what is the middle term? Here it is, watch. You can also use the same method as before, just make your middle term 0. Make your middle term 0. So that means this: a squared plus 0a minus 16. Okay, and trust me now, this will work. Let's use our method as before. So we're thinking about factors of 16. Okay, we've got, we got 4 and 4, or negative 16. I mean, I'm so sorry, negative 16. 4 and negative 4, or negative 4 and 4. And already right away I can see that that's the answer, but we can continue here. So negative 2 and negative 2 and 8, and then 2 and negative 8, and so on and so forth. But look, we're looking for one of these to sum up to 0. And what is that? Well, either one of these, 4 and negative 4, negative 4 and 4, these will give us our answer, okay? 16 is a perfect square, so we're looking for two numbers that are the same. One's positive, one's negative. And our answer will be plus 4 minus 4. And there we go. Let's do another one. What if we have something like a squared minus 9? Take a moment and try and figure this one out yourself. Okay, assuming you've tried, you can rewrite this as a squared plus 0a minus 9, right? If you ever see this type of thing when you only have, two perfect squares, minus sign in between, you just add the middle term and put a 0 coefficient in front of it, okay? Now what will that be? We're looking for two numbers that multiply to 9 that are the same. Well, what are those? They're 3 and 3. So I'm going to go 3 and negative 3, though, because we have a negative 9. So 3 times negative 3 is negative 9. Or negative 3 times a 3. And that really gives us, when we add them together, it gives us our 0 right there. So that means our answer will be a, in our parentheses that is, a plus 3, a minus 3. Okay, And when you multiply this out, you will see that, in fact, you get an a plus 3 and an a minus 3. The a's cancel, the middle term goes away, and then you have a squared minus 9 when you check your answer, when you multiply it out. And so I just wanted to show you guys another method for doing these special cases, but you can use the good old-fashioned method by just adding that middle term with a 0 coefficient in the middle.